Picture, if you will, the universe not as an empty void, but as a living fabric, a tapestry of space-time woven with the threads of gravity. Every star, every planet, leaves a gentle indentation in this fabric, like a pebble dropped into a still pond. But a black hole is something else entirely. It is a point of near-infinite density, a cosmic singularity where a star, once impossibly vast and brilliant, has collapsed under its own weight, punching a hole through the very fabric of reality. It is a whirlpool in the ocean of space-time, a maelstrom of gravity so profound that it captures not only errant stardust and wandering comets, but the fleeting photons of light and the river of time itself. As we approach this cosmic titan, we reach the event horizon, the point of no return. Here, the laws of our everyday experience begin to fray. Time, that relentless, forward-marching soldier, grows weary. It slows, stretches, and dilates. For a traveler orbiting just beyond this threshold, a single heartbeat might correspond to 1,000 years in the universe they left behind. It is a realm of eternal twilight, a golden hour that stretches into infinity. And it is here, in this becalmed ocean of space-time, that we open our minds to a staggering possibility, the existence of life. Not life as we know it, but life as it could be, forged in the crucible of relativity. What kind of civilization could flourish in a place where time itself is a negotiable quantity? Our own existence is a frantic, breathless sprint against oblivion, a brief candle flame flickering in the cosmic wind. But for beings who call this time-dilated sanctuary home, life could be a slow, deliberate, and impossibly long symphony. Imagine a consciousness that does not operate in fleeting electrical impulses, but in grand, geological processes. Picture a society where history is not written in books, but is etched into the slow, patient decay of orbiting mountains, their thoughts taking form over eons. Their cities would not be structures of steel and glass, but might be living organisms woven from the strange, exotic matter that thrives in this extreme gravitational field, their architectures shifting and growing over spans of time that dwarf the age of our own solar system. These beings would be the universe's silent monks, its patient librarians, its eternal observers. From their unique perch at the edge of the abyss, the rest of the galaxy would unfold before them in a breathtaking, accelerated spectacle. They would witness the birth of new stars not as a slow-motion event, but as a sudden blossoming of light. They would see stellar nurseries like the Orion Nebula ignite and fade like embers on a cosmic fire. The majestic collision of our Milky Way with Andromeda, an event 4 billion years in our future, would appear to them as a fluid, graceful dance of light and shadow, a celestial ballet played out in a matter of moments. They would observe the very evolution of the cosmos, its accelerating expansion, the formation of the great cosmic web, the clustering of galaxies, as if watching a time-lapse film of creation itself. Their science, their art, their entire philosophy would be built upon a foundation of what we can only call deep time. Their perspective would be so vast, so impossibly grand, that the entirety of human history would be but a single, instantaneous flash of light in their sky, too brief to be noticed, too fleeting to be understood. They would be the true chrononauts, explorers who travel not through the 3 dimensions of space, but through the 4th dimension of time. The source of their energy would be the very engine of cosmic destruction at their core. The black hole's accretion disk, a swirling, incandescent vortex of gas, dust, and shattered stars spiraling to their doom, would be their sun. It would be a permanent, brilliant dawn, a constant source of unimaginable power, painting their world in the high-energy hues of X-rays and gamma radiation. Here, matter is shredded by tidal forces, releasing energy with an efficiency that dwarfs even the nuclear fusion in our own sun's core. This civilization would have long ago mastered the art of harnessing this cosmic furnace, learning to draw sustenance from the chaos, to shield themselves from its lethal energies. and to build their world in the cradle of a tamed, controlled cataclysm. How would such beings communicate? Sound and light, the mediums of our own hurried conversations, would be fickle and unreliable here, easily distorted, bent, and consumed by the immense gravity. Perhaps their language is something far more profound. Imagine a dialogue conducted through the modulation of gravitational waves, silent, intricate ripples sent through the fabric of space-time itself. A single word in this language might be a complex waveform that takes a century of our time to broadcast. A thoughtful conversation could span the entire lifespan of a star. To them, we would be less than ghosts. We would be like the subatomic particles that fizzle in and out of existence in a quantum foam, ephemeral, chaotic, and fundamentally unreal. As you drift deeper now, let your own perception of time begin to soften and blur. Feel the gentle, irresistible pull of this profound idea. You are a disembodied observer, floating weightlessly at the edge of this time-dilated world. Before you, the light from distant galaxies is bent and warped by the black hole's gravity, creating ghostly arcs, shimmering rings, and multiple, phantom images of the same star, a celestial gallery of gravitational lenses. This is the Einstein Cross, a cosmic mandala illuminating the eternal twilight. You feel a silence here that is deeper than any earthly quiet, the resonant hum of a universe operating on a timescale and a physical scale that transcends our own biology. This is not a realm of simple destruction, as we so often imagine it. It is a place of sublime, ordered power, a cosmic laboratory where the fundamental forces of nature are stretched to their breaking point, and where life, if it were to arise, would have to become something truly, fundamentally alien. These beings would not share our fragile carbon chemistry. They might be crystalline entities, their consciousness encoded in the slow, patient growth of a lattice of exotic matter. Or perhaps they have transcended matter entirely, existing as pure, self-aware energy, their thoughts flowing through the complex, super-strong magnetic fields that web the region, their forms nothing more than the slow, majestic dance of superheated plasma. As we slowly drift away from this world at the edge of time, we carry with us a gift, a new sense of perspective. Our own lives, our planet, our entire civilization, are but one tempo, one melody in a vast, cosmic symphony. There are other rhythms, other harmonies, playing out in the deep, silent corners of the night sky. The universe is not empty. It is a plenum, filled with endless, breathtaking possibilities, each one more wondrous than the last. Let this thought be a blanket of cosmic peace, a profound reminder of the infinite and beautiful mystery in which we are all suspended. Our journey has only just begun. Let us now retract our gaze. We pull back from the edge of the black hole, from that realm of slow, deliberate time, and begin a journey in the opposite direction. We are not moving forward into the deep future, but backward into the deepest past. Let your consciousness be a vessel, sailing on the reverse currents of time, past the formation of Earth, past the birth of our sun, past the first galaxies igniting the darkness. We travel further and further back, through the cosmic dark ages, to a time before a single star had ever shone. We are going home, to the very first moment, to the genesis of everything. Breathe in. And as you exhale, imagine the entire universe, all of its 2 trillion galaxies, its countless stars, its immeasurable voids, all of it collapsing inward. The cosmic film is rewinding at an impossible speed. Space and time, which now seem so vast and boundless, are shrinking, converging, returning to their source. We arrive at a point of origin so profound it defies language. Before this moment, there was no space to occupy, no time to measure. There was only potential. A silent, waiting, infinitesimal point that contained the promise of everything we have ever known and ever will know. This is the threshold of the Big Bang. let go of the image of a violent explosion in a pre-existing void. That is a human concept for a cosmic event that had no witnesses. Instead, picture it as a blossoming. A single, perfect, impossibly hot and dense point that, in an instant, became space and time. It was the birth of reality itself. In the very first fraction of the very first second, the universe began to expand, not like a bomb detonating, but like a breath being released, filling the nothingness with its own existence. And in this first breath, something extraordinary happened: cosmic inflation. In a span of time too small to comprehend, less than a trillionth of a second, the universe swelled at a speed that vastly outpaced the speed of light. It did not violate relativity. It was the fabric of space-time itself that was expanding, stretching from a size smaller than an atom to a volume larger than a galaxy in less than the blink of an eye. This was not a chaotic event, but a moment of sublime and perfect smoothing. Like a crumpled silk sheet being pulled taut in an instant, this hyper-expansion ironed out the wrinkles in the newborn cosmos, laying the foundation for the vast, uniform, and stable universe we see today. It was an act of impossible grace, setting the stage for everything that would follow. Within this nascent, expanding cosmos, the fundamental forces of nature, which now govern our reality with such distinct and separate rules, were merged into a single, unified force. As the universe expanded and its unimaginable temperature began to fall, this unified force began to break apart, like a divine symmetry shattering into the beautiful complexity of our world. First, gravity separated itself from the fold. It was the sculptor, the silent architect, the weakest of the forces, yet the one whose patient, relentless pull would one day gather the mists of hydrogen into stars and shepherd the stars into galaxies. It stepped away to begin its slow, cosmic work. Shortly after, the strong nuclear force broke free. This is the force of binding, the unbreakable glue that would one day hold the hearts of atoms together, overcoming the mutual repulsion of protons. With its emergence, the potential for stable matter was born. Finally, the electroweak force split into its two components: the electromagnetic force, which would govern light, chemistry, and all the interactions of our visible world, and the weak nuclear force, the quiet engine of radioactive decay and a key player in the nuclear fusion that would power the stars. In less than a second, the four fundamental forces had taken on their distinct identities. The cosmic rulebook had been written, and the universe was ready for its next great act, the birth of matter. In this primordial era, the universe was a seething, incandescent soup known as the quark-gluon plasma. It was a state of matter so hot and so dense that the particles we know today could not yet exist. Protons and neutrons had not yet formed. Instead, their constituent parts, the fundamental particles known as quarks, roamed free in a chaotic sea of energy, held together by particles called gluons. Imagine a roiling, vibrant ocean of pure potential, a universe of ingredients before the recipe had been followed. The temperature was measured in the trillions of degrees, a state of energy so extreme that matter as we know it would have instantly vaporized. But the universe continued to expand and, crucially, to cool. As the temperature dropped below a critical threshold, the strong nuclear force, now free to act, began to work its magic. The once free quarks were now compelled to bind together. The universe was undergoing baryogenesis, the formation of the first heavy particles. In groups of 3, quarks began to cling to one another, forming the first stable protons and neutrons. 2 up quarks and 1 down quark formed a proton. 1 up quark and 2 down quarks formed a neutron. These were the first building blocks of matter, the first solid things in a universe of pure energy, forged in the cooling embers of the Big Bang. At the end of this incredible first second, the universe, while still hotter and denser than anything we can imagine, had undergone a series of transformations that set the course for the next 13.8 billion years. The forces were separate. The fundamental rules were established. And the first protons and neutrons, the very particles that make up the nucleus of every atom in your body, had solidified from the primordial energy soup. The stage was now set. The cosmic dust was settling, and the universe was preparing for the next phase of its evolution, the era of nucleosynthesis, when these new particles would begin to combine, forming the nuclei of the very first elements. The universe had taken its first breath, and the great story of cosmic evolution was truly underway. Let us drift now, deeper into that first, incandescent second. We leave behind the grand architecture of the cosmos, the scale of forces and inflation, and we shrink our perspective. We are journeying inward, past the scale of atoms and nuclei, for they have not yet been born. We are going to a place more fundamental, a realm of particles so elusive, so mysterious, that they can never be witnessed in isolation. We are descending into the heart of matter itself, into the world of the quarks. Breathe in the stillness, and with the exhale, feel yourself becoming smaller than a grain of sand, smaller than a microbe, smaller than the wavelength of light. You are entering the quantum realm, a world governed by laws of probability and potential, a world of beautiful and profound strangeness. Here, in the primordial soup of the newborn universe, we find the very essence of the world around us. Quarks are the fundamental notes in the silent symphony of reality. They are the letters in a cosmic alphabet that, when combined in just the right way, write the story of everything we can touch and see. They are the building blocks of the building blocks. Imagine matter as an ancient, sacred text. The universe we see, the galaxies, stars, and planets, are the grand chapters. The elements of the periodic table are the sentences. The atoms are the words. But the quarks are the ink itself, the elemental characters from which all meaning is derived. Yet, there is a profound rule to this quantum world. A single quark can never be found alone. Like a magnetic pole, which must always have a north and a south, a quark is forever bound to its brethren, held in an embrace so powerful that no force in the universe can tear them apart. They are the ultimate hermits, living only in groups, their individual existence forever hidden from our direct view. To understand their story, we must return to that sliver of time just after the Big Bang, a period known as the quark epoch. This was a time when the universe was so unimaginably hot, so intensely dense, that the very idea of structure was impossible. For a brief, fleeting moment, the universe existed as a quark-gluon plasma. This was matter in its most liberated and chaotic state. It was a scalding, vibrant sea of energy where quarks and their counterparts, the gluons, moved freely, untethered by the rules that would later govern them. It was a universe without form, a roiling soup of primordial potential. The temperatures, in the trillions of degrees, were too extreme for the strong nuclear force to take hold. The universe was a frantic, energetic dance of free particles, a cosmic storm of pure becoming. In this plasma, the gluons acted as the carriers of the yet untamed strong force. Picture them as shimmering, energetic messengers, the very essence of the cosmic glue that would one day bind the universe together. But in this heat, their glue could not set. The quarks, in their 6 flavors, the familiar up and down, and their more exotic, heavier cousins, charm, strange, top, and bottom, swirled in a state of perfect, chaotic freedom. This was the universe before the first stone was laid, before the first atom was conceived. It was a moment of pure, undifferentiated being. But as cosmic inflation stretched the universe, a great cooling began. This cooling was the most important event in the early life of the cosmos. As the temperature of the quark-gluon plasma dropped, it crossed the critical threshold. The thermal energy that had kept the quarks in their frantic, free dance began to subside. And in its place, the strong nuclear force, the most powerful of the four fundamental forces, finally began to assert its dominance. It was a moment of profound transformation, a great crystallization in the history of the cosmos. The chaos began to yield to order. Across the universe, the free-roaming quarks were now compelled by the strong force, carried by the gluons, to bind together. The period of confinement had begun. No longer could a quark exist on its own. It was drawn inexorably to its neighbors, forming stable, composite particles in groups of 2 or 3. It was the first true act of creation, the moment that matter, as we know it, began to take shape from the fire. The universe was no longer just a soup of ingredients. It was now a kitchen where the first, most fundamental recipes were being followed. From this cosmic binding, 2 of the most important particles in our universe emerged: protons and neutrons. These are the particles that would go on to form the nucleus of every atom in existence. And their properties were determined by a simple, elegant combination of quarks. A proton, the particle that would give an atom its identity, was formed from 2 up quarks and 1 down quark. This specific combination gave it a positive electrical charge. A neutron, its slightly heavier sibling, was formed from 2 down quarks and 1 up quark, a recipe that resulted in a particle with no charge at all. This subtle difference, born from a simple cosmic recipe, is the foundation for all of chemistry, all of biology, all of life. The positive charge of the proton would later capture the negative charge of the electron, forming the first stable atoms. The neutrality of the neutron would allow nuclei to hold together, providing the stability for elements heavier than hydrogen to exist. All of the complexity and beauty of our world rests upon this simple, foundational pairing of up and down quarks in the first second of time. As you continue to drift in the quiet darkness, reflect on this. The very floor beneath you, the air you breathe, the body you inhabit, all of it is composed of atoms. And at the heart of every one of those atoms are protons and neutrons. And within every one of those protons and neutrons are quarks, forever bound together by the strong force, ancient relics from the first second of the universe's life. You are made of the same primordial matter that was forged in the cooling embers of the Big Bang. The fundamental rules that lock these tiny, elusive particles together are the same rules that give you form and substance. The universe is not something separate from you. You are a part of its unfolding story, a vessel of cosmic history, carrying the memory of the quark epoch within every cell of your being. We have witnessed the birth of the first particles, the quarks, and seen them bind together into the protons and neutrons that form the bedrock of our material world. But what compelled them to do so? What rules governed this first act of cosmic creation? Let us now pull our focus back, away from the particles themselves, and turn our attention to the invisible laws they obey. We are exploring the grand, silent architects of the universe, the 4 fundamental forces. Breathe slowly, and feel the gentle, persistent pull of gravity holding you softly in your bed. This is the oldest and most familiar of the forces, a constant, silent companion in our lives. But in the first moments of creation, gravity was not alone. It was not distinct. In the unimaginable heat and energy of the universe's first instant, all the forces we know today were merged into one. There was a single, perfect, unified force, a state of sublime and unbroken symmetry. It was the master blueprint from which all of physical law would be drawn, a single, pure note that held within it the potential for the entire symphony of the cosmos. As the universe expanded and cooled with impossible speed, this perfect symmetry began to break. Imagine a surface of water, perfectly still and uniform, suddenly freezing. As the ice crystals form, they create patterns and structures, breaking the uniformity of the liquid. so too did the forces of nature crystallize from the primordial energy of the universe. In a series of graceful separations, the unified force differentiated, giving birth to the four distinct rulers of our cosmos. The very first to separate was gravity. It stepped away from the unified fold to begin its eternal, patient work. Gravity is the master sculptor of the cosmos, working on the grandest of scales. While it is the weakest of the four forces, its reach is infinite. It was gravity's gentle but relentless pull that first gathered the primordial gas into the clumps that would become the first stars and galaxies. It is the force that dictates the graceful waltz of planets around their stars and stars around the hearts of their galaxies. It is the unseen hand that weaves the cosmic web, that vast, filamentary structure of galaxy clusters that forms the backbone of the universe. Gravity is the force of structure, of gathering, of cosmic architecture. It works slowly, quietly, but over the eons, its influence is absolute. Next to separate from the unified force was the strong nuclear force. If gravity is the architect of the large, the strong force is the master of the small. It is the most powerful of the forces, but its influence extends only across the infinitesimal distances within the nucleus of an atom. Its role is simple and profound: to bind. It is the unbreakable chain that holds quarks together inside of protons and neutrons. And it is the force that clamps those protons and neutrons together to form a stable atomic nucleus, overcoming the powerful electromagnetic repulsion that tries to force the positively charged protons apart. Without the strong force, the elements, carbon, oxygen, iron, could never exist. The universe would be nothing but a thin, formless hydrogen gas. The strong force is the source of all material stability, the heart of all substance. As the universe continued to cool, the final split occurred. The electroweak force divided into two, giving us the last pair of our cosmic quartet. First came the weak nuclear force. This is the force of transformation. It is the quiet alchemist of the cosmos, governing processes like nuclear fusion and radioactive decay. While the strong force binds the nucleus together, the weak force can change its very nature, turning a neutron into a proton or vice versa. This is the process that powers the stars. Inside the core of our Sun, the weak force allows hydrogen nuclei to fuse into helium, releasing the light and heat that sustains our world. Over the lifetime of a star, it facilitates the creation of heavier and heavier elements. The weak force, though subtle, is the engine of stellar evolution and the creator of chemical diversity in the universe. Finally, there was electromagnetism. This is the force of our everyday experience, the force of our senses. It is the light that travels from distant stars to reach your eyes. It is the energy that flows through the circuits of your brain as you listen to these words. It governs the interactions between all charged particles, holding the electrons in their orbits around atomic nuclei. It is the force of chemistry, allowing atoms to bond together to form molecules, to create water, air, rock, and the complex organic structures of life itself. Electromagnetism is the great messenger of the cosmos, the artist that paints the universe with light and color, and the weaver that allows simple atoms to form the intricate tapestry of our world. These four forces, gravity, the strong nuclear force, the weak nuclear force, and electromagnetism, are the pillars upon which our universe is built. Once separated, their intricate interplay began to choreograph the evolution of everything. Their combined influence allowed the first atoms of hydrogen and helium to form, making the universe transparent to light for the first time and releasing the afterglow we now see as the cosmic microwave background radiation. Gravity pulled matter together to form stars, while the weak and strong forces ignited the nuclear furnaces within them. And electromagnetism carried their light across the expanding void. So as you lie here, feel the presence of these four silent partners. Feel the gravity that gives you weight. Acknowledge the strong force that gives you substance. Be aware of the weak force, working in the slow decay of elements deep within the earth. And see with your mind's eye the electromagnetism that carries the light of the moon and stars to your window. You are not separate from these laws, you are a living expression of them. They are the invisible framework of your being, the ancient, cosmic rules that allow you to be here, now, drifting peacefully into sleep. Let us now move forward in time. We leave behind the frantic, foundational first seconds of the universe and drift across a vast expanse of time. For nearly 400,000 years, the cosmos remained a glowing, opaque fog. Though the fundamental forces were now distinct and the first protons and neutrons had been forged, the universe was still too hot, too energetic, for the next great step in creation to occur. It existed as a vibrant, seething plasma, a universal sea of charged particles. Breathe in, and imagine this young cosmos. It is not dark, but brilliantly aglow in all directions. A boundless ocean of free-roaming protons, helium nuclei, and crucially, a frantic swarm of unattached electrons. Light, in the form of photons, existed in abundance, but it could not travel freely. A photon would emerge, only to collide instantly with a free electron, be absorbed, and sent careening in a new direction. It was like being lost in a fog so dense that a beam of light is scattered into nothingness just inches from its source. The universe was full of light, but it was a prisoner of the plasma. There was no view, no distance, no clear path from one point to another. The entire cosmos was a single, luminous, impenetrable cloud. But the universe continued its patient, relentless expansion. And with that expansion came cooling. Over these hundreds of thousands of years, the temperature of the cosmos gradually dropped, approaching a magical threshold. The frantic energy of the electrons, which had kept them forever flitting away from the grasp of the protons, began to subside. And then, at a moment preordained by the laws of physics, the universe was cool enough for the first great act of chemistry to occur. This was the era of recombination. Imagine it as a great, silent, cosmic courtship, happening everywhere at once. The positive charge of the protons and helium nuclei began to exert an irresistible pull on the now calmer, negatively charged electrons. An electron would drift near a proton, and instead of ricocheting away, it would be captured, falling into a stable orbit around the nucleus. In that moment, the first neutral atom of hydrogen was born, one proton, one electron, bound together by the force of electromagnetism. Across the entirety of space, this was happening. Trillions upon trillions of these simple, elegant atoms were forming, transforming the very nature of the universe. Shortly after, the slightly more complex helium nuclei, 2 protons and 2 neutrons, also began to capture their own electrons, 2 for each nucleus, forming the first neutral atoms of helium. These 2 elements, hydrogen and helium, born in this era, would go on to make up more than 99% of all the visible matter in the universe for the rest of time. They were the primary result of the Big Bang, the foundational materials from which all future complexity would be built. The formation of these first atoms was the turning point that changed everything. With the free electrons now captured and bound within neutral atoms, the primary obstacle for light was gone. The dense fog that had filled the universe for millennia suddenly lifted. In an instant, the cosmos became transparent. The photons, the particles of light, were now free to travel across the expanse of space, unimpeded, on journeys that would last for billions of years. Picture that moment. It was the first sunrise of the universe. The light that was present everywhere could now travel from everywhere. This ancient light, released in this era of recombination, is still traveling today. Stretched by the expansion of space over 13.8 billion years, it now reaches us not as visible light, but as a faint, cool glow of microwaves. The cosmic microwave background radiation. When our telescopes detect this faint hum, they are capturing the fossil light from this very moment, the universe's first baby picture, a snapshot of the instant it became clear. But the story of creation did not stop there. With the formation of stable atoms, the universe had learned a new secret. It could now take another step toward complexity. As the transparent universe continued to cool, these new, neutral hydrogen atoms could now approach each other. Occasionally, two hydrogen atoms would draw close enough to share their electrons, forming a stable bond. In this simple pairing, the first molecule was born, molecular hydrogen, or H2. This was a monumental event. It was the dawn of chemistry. The universe had moved from physics, the world of forces and particles, to chemistry, the world of bonds and structures. This simple H2 molecule, though seemingly insignificant, would play a critical role in the next chapter of cosmic history. Molecular hydrogen is an incredibly efficient coolant. As the first clouds of primordial gas began to clump together under gravity, the presence of H2 allowed them to radiate away their heat, cooling down and collapsing much more efficiently. These collapsing clouds would become the nurseries for the very first stars. The formation of this first, simple molecule was the key that unlocked the door to a universe filled with starlight. As you rest here, in the quiet of your room, let this story of emerging clarity soothe you. The universe, in its infancy, transformed itself from a chaotic, opaque plasma into a calm, transparent sea of simple atoms and molecules. It was an evolution from blinding fog to clear sight, from a hot, frantic soup to the cool, ordered potential that would set the stage for the first stars, the first galaxies, and eventually for us. We now drift into an era of profound stillness. The universe is transparent, filled with the simple, newly formed atoms of hydrogen and helium. The frantic energy of the plasma age has passed. For hundreds of millions of years, the cosmos will enter a period known as the Cosmic Dark Ages, a time before the first stars ignited. But the light from the universe's first dawn, the moment of recombination, is now free, and it has begun an immense journey across space and time. We turn our attention now to this light, this echo of creation. It is the cosmic microwave background radiation. Imagine you are standing in the quietest place imaginable, and you begin to hear a faint, impossibly soft hum. It is not coming from any particular direction, but from everywhere at once. It is perfect in its consistency, a single, pure note that fills all of space. This is the closest analogy for the cosmic microwave background. It is the afterglow of the Big Bang, the oldest light in the universe, bathing everything, including you, in its ancient, gentle radiance. It is the fading warmth of creation's first fire, stretched and cooled by billions of years of cosmic expansion until it is now just a few degrees above absolute zero. For most of human history, we were completely unaware of this relic. Then, in the mid-1960s, two astronomers, Arno Penzias and Robert Wilson, were using a large radio antenna and were troubled by a persistent, low-level hiss in their data. It was a noise that would not go away. They pointed their antenna to different parts of the sky. They took measurements day and night. They even cleaned their equipment of pigeon droppings, thinking it might be the cause. But the hiss remained, faint, constant, and coming from every corner of the cosmos. They had, by complete accident, stumbled upon the most profound discovery in modern cosmology. They were not listening to noise from their equipment or from the Earth. They were listening to the echo of the Big Bang itself. This discovery was the cornerstone of evidence for a universe that began in a hot, dense state. It was a tangible link to our own origin, a snapshot of the infant cosmos when it was only about 380,000 years old. This is the universe's first baby picture. Before this light was released, the universe was an opaque fog. After, it was a clear, dark space filled with neutral atoms. The CMB is the photograph of that exact transition. It is a window that allows us to look back in time, to see the conditions of the cosmos before the first star ever twinkled, before the first galaxy had ever formed. And when we look closely at this photograph, we find that it is not perfectly uniform. While the temperature of the CMB is astonishingly consistent across the sky, at about 2.7 Kelvin, there are minuscule variations. Tiny, almost imperceptible ripples in the temperature, differences of only a few millionths of a degree. And in these tiny imperfections lies the secret to our own existence. These are not flaws in the picture, they are its most important feature. These slight temperature fluctuations correspond to regions in the early universe that were infinitesimally denser or less dense than their surroundings. The slightly denser regions, the warmer spots in the CMB, represent the seeds of cosmic structure. They were the gravitational wells, the points of subtle invitation where matter would begin to gather over the next hundreds of millions of years. From these tiny, primordial seeds, the first stars would sprout. Around them, the first galaxies would coalesce. And from them, the vast filaments of the cosmic web would be woven. Every galaxy, every star, every planet, and every living being in the universe today owes its existence to these faint, ancient ripples in the afterglow of creation. They are the ghostly blueprints of the cosmos. By studying the patterns in these fluctuations, scientists have been able to reverse engineer the cosmic recipe. They have determined the very ingredients of our universe. They found that the matter we know, the stuff of stars and planets and ourselves, makes up a mere 5% of the cosmos. A much larger portion, about 25%, is a mysterious, invisible substance we call dark matter, which provided the gravitational scaffolding for galaxies to form. And the vast majority, nearly 70%, is an even more enigmatic force known as dark energy, which is causing the very expansion of the universe to accelerate. The CMB revealed to us that we live in a universe dominated by substances we do not understand. Furthermore, this ancient light acts as a cosmic clock. By measuring the properties of the CMB, we have been able to determine the age of the universe with incredible precision, approximately 13.8 billion years. It also tells us about the shape of the universe itself. The patterns suggest that, on the largest scales, the universe is flat, meaning that parallel lines will remain parallel forever, a geometry that has profound implications for the ultimate fate of the cosmos. So, as you lie here, drifting deeper into a state of peace, imagine this light. This ancient, cool, microwave hum is passing through the room, passing through you, at this very moment. It is a silent, invisible connection to the dawn of time. You are bathed constantly in a relic from the universe's first great exhalation. It is the memory of the cosmos, and it whispers a story of origins, of infinitesimally small seeds growing into a forest of galaxies, and of a universe with a beauty and a mystery far grander than we can ever fully grasp. The universe is now clear, but it is also dark. The ancient light of the cosmic microwave background has been released, and it journeys on, but no new light is being created. The cosmos has entered a profound and lengthy twilight, a period of quiet gestation that would last for hundreds of millions of years. This is the cosmic dark ages. Breathe deeply, and let your mind settle into this immense, patient darkness. The universe is now a vast, expanding, and silent space, filled almost entirely with a diffuse, cooling fog of neutral hydrogen and helium gas. There are no stars to warm the void, no galaxies to pinwheel in the darkness, no planets, no life. It is a universe of profound simplicity and silence. A cosmos waiting for its next great act. The frantic energy of its birth has passed, and now, a long, quiet night has fallen. But this darkness is not empty, and it is not idle. The seeds of structure, those tiny ripples of density we saw in the cosmic microwave background, are still there. And the most patient of all the cosmic architects, gravity, is at work. In the deep silence of this era, gravity is the only force making a difference on a grand scale. It begins to pull, gently and relentlessly, on these regions of slightly higher density. Where the fog of hydrogen is just a fraction of a percent thicker, gravity's pull is a fraction of a percent stronger. Over millions upon millions of years, this tiny advantage begins to matter. The mists of the cosmos are slowly, silently, beginning to gather. And they are gathering upon an invisible scaffold. For the universe, as we have learned, is mostly composed of a mysterious, unseen substance, dark matter. This matter does not interact with light, so it was not buffeted by the intense radiation of the early universe. It was free to begin clumping together far earlier than the normal, visible matter. Unaffected by the pressures that kept the hydrogen gas diffuse, the dark matter began to collapse under its own gravity, forming vast, invisible halos, like great, spherical spider webs in the cosmic darkness. These dark matter halos became the gravitational cradles of the universe, the deep wells into which the visible cosmos would be born. The neutral hydrogen and helium gas, the ordinary matter that would one day form everything we can see, now felt the powerful gravitational pull of these invisible halos. The gas began to drift, to flow along unseen cosmic rivers, into these deep gravitational wells. Over tens of millions of years, vast clouds of this primordial gas accumulated within the dark matter halos, growing ever denser and more compact. These were the first true cosmic nurseries, forming in the blackness, preparing for the dawn. Inside the densest parts of these clouds, a new threshold was being approached. As gravity pulled the gas inward, the pressure and temperature at the core of the cloud began to rise. The atoms were squeezed closer and closer together, the heat growing from hundreds to thousands, then to millions of degrees. The cloud was contracting, its core becoming a glowing, embryonic protostar. And then, after an age of darkness, a new fire was lit. When the temperature at the core reached about 10 million degrees, the conditions for nuclear fusion were met. The protons of hydrogen atoms were slammed together with such force that they fused, igniting in a blaze of creation and releasing a tremendous amount of energy. The first star was born. This was the true dawn of the universe. A point of new light in an ocean of black. And it was not alone. Across the cosmos, in the hearts of the densest clouds, thousands, perhaps millions, of these first stars were igniting. These were not stars like our sun. They were the population 3 stars, celestial giants forged only from the pure hydrogen and helium of the early universe. They were hundreds of times more massive than our sun, and because of their immense mass, they burned with a brilliant, blue-white intensity, 1,000,000 times more luminous than the stars we see today. They were magnificent, and they were short-lived. The intense, ultraviolet light from these first stellar giants blazed out into the surrounding darkness, and it began to transform the universe once more. This powerful radiation struck the neutral hydrogen atoms that filled the cosmos, stripping them of their electrons. The universe, which had become neutral during the era of recombination, was now being reionized by the light of its first children. The cosmic dark ages were coming to an end. The fog of neutral gas was being burned away, making the universe transparent in a new way, not just clear, but illuminated. This period of cosmic reionization marked the end of the universe's long, quiet night. The light from the first stars and the galaxies they began to form would now travel freely, beginning the rich, complex, and luminous history of the cosmos we inhabit today. The darkness was not an ending, but a necessary, patient beginning. It was the time when the invisible forces of gravity and dark matter did their silent, foundational work, preparing the stage for the glorious entrance of starlight. The long, quiet night of the cosmic dark ages is now over. The universe, for the first time, is filled with new light, kindled in the hearts of its firstborn stars. We drift now into an era of fire and creation, a time when the cosmos was a brilliant, violent, and magnificent forge, shaping the very matter that would one day lead to us. This is the story of the first stars and the dawn of the first galaxies. Breathe, and picture the scene. Across the vast, dark canvas of the cosmos, points of brilliant, blue-white light have appeared. These are the population 3 stars, the first generation of stellar giants. They are unlike any star in our modern sky. Forged from the pure, unadulterated hydrogen and helium of the early universe, they are immaculate creations, free from the heavy elements that enrich their descendants. Because of their simple composition, they grew to colossal sizes, hundreds of times more massive than our own sun. And because of this immense mass, they burned with an intensity that is difficult to comprehend, 1,000,000 times brighter than our sun, blazing with a fierce, hot, ultraviolet light. They were glorious, and their lives were fleeting, a brief and spectacular chapter in the cosmic story. Inside the cores of these first stars, the universe was learning a new form of alchemy. The incredible pressures and temperatures ignited the process of nuclear fusion, slamming hydrogen nuclei together to create helium. But for these giants, that was only the beginning. As they burned through their hydrogen fuel, their cores contracted further, becoming even hotter and denser, allowing them to fuse helium into heavier elements. For the first time, the universe was creating carbon. It was creating oxygen, nitrogen, silicon, and eventually iron. These were the elements of life, the building blocks of rocky planets and complex molecules. And they were being forged for the very first time in the hearts of these colossal, short-lived stars. The universe was no longer just a simple space of gas. It was now a cosmic forge, creating the raw materials for its own future complexity. But the most creative act of these first stars was their death. Because they were so massive, none of them died quietly. After only a few million years, a brief moment on cosmic timescales, they exhausted their nuclear fuel. Their cores collapsed catastrophically under their own immense gravity, triggering the most powerful explosions the universe had ever known, supernovae. In a final, brilliant flash that could outshine a small galaxy, these stars tore themselves apart. This was not an act of mere destruction. It was an act of profound generosity. In these supernova explosions, all the heavy elements that had been forged in the stellar cores, the carbon, the oxygen, the iron, were blasted out into the surrounding space. The death of the first stars seeded the cosmos with the building blocks of everything that would come after. This was the first great enrichment. The pristine gas of the early universe was now being salted with the potential for planets, for life, for us. Every atom of carbon in your body, every atom of oxygen you breathe, was forged in the heart of a star and scattered in a supernova explosion just like these. These first stars were born in clusters, nestled within the gravitational embrace of their dark matter halos. And as they lived and died, gravity continued its patient work, pulling these clusters of brilliant, massive stars closer together. These were the seeds of the first galaxies. They were not the grand, spiral galaxies we know today. They were small, clumpy, chaotic assemblies of stars and gas, glowing fiercely with the light of their stellar nurseries. They were proto-galaxies, the first islands of light in the cosmic ocean, growing by pulling in more gas and by merging with each other in the dense nodes of the cosmic web. And as these first galaxies grew, the collective light of their millions of stars completed the great transformation of the universe. The process of cosmic reionization, begun by the first individual stars, was now being driven by entire galaxies. Bubbles of ionized, transparent gas grew around each galaxy, expanding and merging with one another. Over a period stretching from about 150 million to a billion years after the Big Bang, these bubbles merged completely, and the last vestiges of the neutral hydrogen fog that had defined the dark ages were burned away. The universe had finally become the transparent, starlit expanse that we know today. So as you drift towards sleep, think of this cycle of creation. The first stars had to live brief, violent lives and die in spectacular fashion so that the universe could become interesting. Their death was not an end, but the critical step that allowed for a universe of rocky planets, of complex chemistry, and of life. You are made from the ashes of these first stellar giants. Their legacy is written in your bones, in your blood, in your every breath. We have witnessed the birth of the first stars and the dawn of the first galaxies, islands of brilliant light in the vast, expanding universe. But as we watch these nascent structures grow, a profound question emerges. What held them together? What guided the primordial gas into the dense configurations needed for stars to form? The answer is a substance that is both everywhere and nowhere, the silent, invisible partner in the cosmic dance, dark matter. Let your mind be open now to the unseen. We are entering a realm of cosmic mystery. Imagine that for every particle of matter you can see and touch, every atom in every star, planet, and cloud, there are 5 other particles that are completely invisible. They do not shine, they do not reflect light, they do not cast a shadow. They are a form of matter that does not interact with the force of electromagnetism, and so they are utterly, permanently dark. This is dark matter, and it is the true gravitational backbone of our universe. It makes up about 85% of all the matter in the cosmos, a ghostly, silent majority that outweighs everything we can see by more than 5 to 1. We know it exists not by seeing it, but by feeling its presence. Astronomers, when they look at distant spiral galaxies, see them spinning. But they are spinning far too quickly. The outer stars are moving at such tremendous speeds that the gravitational pull of the visible stars and gas should not be enough to hold them in their orbits. The galaxies should fly apart, their stars flung into the intergalactic void. The only thing holding them together is the immense, unseen gravity of a vast halo of dark matter, surrounding and pervading the entire galaxy. Dark matter is the invisible anchor that gives galaxies their form and stability. Its role, however, began long before the first galaxy ever formed. To understand its importance, we must journey back again to the era just after the Big Bang. In the hot, dense, early universe, normal matter, the protons and electrons, was constantly battered by an intense bath of radiation. It was like a furious cosmic wind that prevented the normal matter from collapsing under gravity. But dark matter, being invisible to light and radiation, felt no such pressure. It was immune to this storm. And so, it had a head start. While normal matter was kept diffuse and smooth, the particles of dark matter were free to respond to the one force they obey, gravity. They began to clump together, slowly at first, but with gathering momentum. Over millions of years, they formed vast, spherical clouds, dark matter halos. These were the first large structures in the universe, invisible gravitational wells, cosmic anchors forming in the darkness. They were the invisible scaffolding upon which the visible universe would later be built. These halos did not form in isolation. They were connected by immense, long filaments of dark matter, creating a colossal, universe-spanning network, the cosmic web. Imagine a spider's web on a cosmic scale, stretching for billions of light years. The long, sticky threads are the filaments of dark matter. And the points where the threads intersect are the massive, dense halos. The universe, on its largest scale, is not a random assortment of galaxies, but a beautiful, intricate web-like structure. And it was into this pre-existing, invisible structure that normal matter was finally drawn. As the universe cooled and the pressure from radiation subsided, the hydrogen and helium gas began to feel the irresistible pull of the deep gravity wells carved out by the dark matter halos. The gas flowed along the cosmic filaments like rivers, streaming into the halos where it could finally cool, condense, and fragment. It was in the very heart of these dark matter halos that the gas clouds became dense enough to ignite and form the first stars. The galaxies we see today are like luminous dewdrops that have condensed upon the invisible threads of the cosmic web. This ghostly architect continues to shape our cosmos. Dark matter is the gravity that binds galaxy clusters together, vast cities of galaxies that would otherwise drift apart. It is the hidden mass that bends the light of distant objects, allowing us to map its presence through gravitational lensing. Its influence is everywhere, yet its nature remains one of the most profound and humbling mysteries in all of science. We do not know what it is. Physicists have proposed various candidates, exotic particles known as WIMPs or axions, and they have built incredibly sensitive detectors deep underground, hoping to catch the whisper of a single dark matter particle passing through the Earth. But so far, the ghost remains unseen. As you drift now, in the quiet and the dark, picture this invisible architecture all around you. Our galaxy, our solar system, even the atoms in your body, are all held within a vast, invisible halo of this mysterious substance. We are living inside a structure we cannot see, a silent testament to the fact that the universe is so much grander and so much stranger than what is revealed to our eyes alone. We have seen how the invisible architecture of dark matter created the great cosmic web and gathered the primordial gas into the first galaxies. Let us now zoom in. We focus our consciousness on one of these young galaxies, and we drift towards a region of profound darkness within it. It looks like a hole in the fabric of the stars, but it is not empty. It is a vast, cold, and serene cloud of gas and dust. It is a stellar nursery, a molecular cloud, and it is here that new suns are born. Breathe, and imagine yourself floating in the heart of this cloud. It is a place of deep quiet and cold. The temperature here is only a few degrees above absolute zero. The cloud is composed almost entirely of the simplest element, hydrogen, now often bound into pairs as molecular hydrogen. And mixed in with this gas is a fine mist of dust, tiny grains of carbon and silicates, the very dust that was forged in the hearts of the first stars and scattered by their supernova deaths. This cloud is a repository of cosmic potential, a place of waiting. For millions of years, this cloud can drift in a state of delicate balance, with the gentle outward pressure of its gas preventing a total collapse under its own gravity. But this balance is fragile. All it takes is a nudge. Perhaps the shockwave from a nearby supernova ripples through the cloud, or the gravitational pull of a passing star stirs its contents. Whatever the trigger, a region within the cloud begins to contract. Gravity begins to win. Slowly, inexorably, the cloud starts to fall inward upon itself. As the material collapses, the cloud fragments into smaller, denser cores. Let us follow one. At its center, the gas particles are squeezed closer and closer together, and as they are compressed, they heat up. After tens of thousands of years of collapse, a glowing, embryonic object forms at the core, a protostar. This is not yet a true star. It shines, not with the fire of nuclear fusion, but with the heat generated by its own gravitational contraction. It is a star in gestation, a glowing ember in the heart of the dark cloud, steadily pulling in more gas and dust from its surrounding cocoon, growing in mass and in heat. The protostar continues to grow for thousands of years, its core becoming ever denser, ever hotter. The pressure is unimaginable. The temperature climbs, from thousands to millions of degrees. The core is now a cauldron of hydrogen nuclei, stripped of their electrons, being crushed together with unbelievable force. And then, the critical moment arrives. The temperature at the very center of the protostar reaches the magic number, 10 million degrees Celsius. At this temperature, the electrostatic repulsion that keeps the positively charged hydrogen nuclei apart is finally overcome. The nuclei slam into each other and fuse, forging a new, heavier nucleus of helium. In this act of fusion, a tiny amount of mass is converted into a tremendous amount of energy. A fire is lit in the heart of the cloud, a nuclear furnace that will burn for millions, or even billions, of years. The protostar has become a star. It is born. This new energy, blazing outward from the core, creates a powerful pressure that pushes against the inward crush of gravity. The star finds a perfect, stable equilibrium. The outward push of fusion and the inward pull of gravity enter into a delicate, lifelong balancing act. This is the state our own sun is in now, a state known as the main sequence. It is the long, stable adulthood of a star, where it will calmly burn its hydrogen fuel for the vast majority of its life. The final mass of the new star depends entirely on how much gas and dust it was able to gather from its parent cloud before its nuclear furnace ignited and the resulting stellar wind blew the remaining material away. If it gathered a small amount of material, it becomes a small, cool, red dwarf, a star that will sip its fuel and shine steadily for trillions of years. If it gathered a huge amount of material, it becomes a massive, hot, blue giant, a star that will burn through its fuel with reckless abandon and live for only a few million years. Our sun is a happy medium, a yellow dwarf with enough fuel for a stable life of about 10 billion years. And these stars are rarely born alone. Within a single, vast molecular cloud, hundreds or even thousands of these collapsing cores can form at once. Stars are born in families, in stellar clusters. They emerge from their dusty cocoon together, a brilliant association of siblings that will drift through their galaxy, a shining testament to the creative power of a simple, cold cloud of gas and the patient, unyielding force of gravity. A star is born, a stable, shining beacon in the cosmos. It has entered its long and peaceful adulthood, the main sequence, a state of perfect balance between the inward crush of gravity and the outward fire of nuclear fusion. For billions of years, it will steadily convert the hydrogen in its core into helium, releasing the light and energy that illuminates its corner of the galaxy. But this fuel is not infinite. And when it begins to run low, the star will embark on its final journey, a transformative path of aging and death that is determined from the very moment of its birth by a single factor, its mass. Let us now follow the two great paths of a star's life cycle. First, we will travel the path of a star like our own sun, a low-mass star. For about 10 billion years, it lives a calm and predictable life. But eventually, the hydrogen in its core is exhausted. The nuclear furnace sputters, and the delicate balance is broken. Without the outward pressure of fusion, the core begins to collapse under its own gravity, becoming hotter and denser. This new heat ignites a shell of hydrogen burning around the now inert helium core. The star's energy output increases dramatically, and its outer layers begin to swell to an enormous size, expanding 100 times or more beyond their original diameter. As these layers expand, they cool, and the star's color shifts to a deep, glowing red. It has become a red giant. It is the autumn of the star's life, a final, grand phase of swelling beauty. After a time, the core becomes hot enough to begin fusing helium into carbon and oxygen. But for a star of this size, this is the end of the line. It does not have enough mass to create the pressures needed to fuse heavier elements. The star becomes unstable, and in a series of gentle pulses, it begins to exhale its outer layers into space. This slowly expanding cloud of gas, illuminated by the hot, dying core, creates one of the most beautiful objects in the cosmos, a planetary nebula. They are the stellar ghosts, intricate, glowing shrouds of gas that take on ethereal shapes like butterflies or cosmic eyes. They are the star's final, peaceful sigh. And what is left behind at the center of the nebula is the star's remnant, a white dwarf. It is the hot, incredibly dense core of carbon and oxygen, a star compressed to the size of the Earth. No longer producing any new energy, it is a cosmic ember, shining only with its leftover heat. Over trillions of years, longer than the current age of the universe, this white dwarf will slowly cool and fade, eventually becoming a cold, dark cinder of crystallized carbon, a black dwarf, a true stellar ghost lost in the darkness. Now, let us turn to the second path, the far more dramatic life of a star born with many times the mass of our Sun. These giants live fast and die young. They burn through their fuel with ferocious intensity, shining with a brilliant blue-white light. Like their smaller cousins, they eventually exhaust the hydrogen in their cores. But their immense mass and gravity lead to a far more spectacular end. They swell into red or blue supergiants, and their cores become hot enough to fuse not just helium, but a whole sequence of heavier elements. The core of a massive star, in its final days, resembles an onion. At the center is a core of newly created elements, surrounded by a shell fusing the previous element, and so on, all the way to an outer shell of hydrogen. The star forges helium, then carbon, then oxygen, then neon, magnesium, silicon, all the way up the periodic table until it creates a core of pure iron. And iron is the end of the road. The fusion of elements lighter than iron releases energy, which supports the star against gravity. But the fusion of iron consumes energy. The furnace at the heart of the star is not just extinguished, it begins to actively drain the star of its energy. The balance is catastrophically broken. In less than a second, the iron core, no longer able to support the crushing weight of the star's outer layers, collapses. The core, with a mass greater than our Sun, shrinks to the size of a city, triggering a shockwave that rebounds outward with unbelievable force. The star detonates in a supernova explosion, one of the most energetic events in the universe. For a few weeks, this single dying star can outshine its entire home galaxy of 100 billion stars. This explosion is not just powerful, it is creative. The extreme energies of the supernova forge all the elements heavier than iron, the silver, the gold, the lead, the uranium, and blast them, along with all the other elements the star created in its lifetime, far out into the cosmos. And what remains of the core? If the original star was massive, the collapse crushes the core into a neutron star, an object so dense that a single teaspoon of its material would weigh 1 billion tons on Earth. If the star was truly a giant, gravity overwhelms all other forces, and the core collapses completely into a singularity, creating a black hole, a point in spacetime from which not even light can escape. The life cycle of a star is the engine of cosmic recycling. The gentle winds of a dying sun-like star and the violent explosion of a supernova enrich the universe with the heavy elements necessary for the next generation of stars, for rocky planets, and for life. The star must die so that the universe can live. We have followed the life of a star from its birth in a cold, dark cloud to its final, transformative end. Now, we will delve deeper into the most creative act of that life cycle, the cosmic alchemy that created the very substance of our world. The early universe, in its simplicity, offered only two main ingredients, hydrogen and helium. Every other element, every substance that makes our world solid and our lives possible, had to be forged. And the forges were the hearts of the stars. Breathe. And let us journey into the core of a star. Here, under pressures and at temperatures beyond all earthly comparison, the universe performs its most fundamental magic. This process is called nucleosynthesis. It begins with the simplest step, the one that powers a star like our Sun for its entire life, the fusion of hydrogen into helium. This reaction releases a tremendous amount of energy, the energy that we see as starlight, the energy that warms our planet. For billions of years, this is a star's primary purpose. But in stars more massive than our Sun, the story continues. When the hydrogen in the core is gone, the star begins to fuse helium. In a process of sublime elegance, 3 helium nuclei are fused together to create a single nucleus of carbon. This is a pivotal moment in cosmic history. Carbon, with its unique ability to form long, stable chains, is the backbone of all known life. And it was created here, in the heart of a dying star. As the star ages, its core gets even hotter, allowing it to climb the next rungs of the cosmic ladder, fusing carbon and helium to make oxygen. In the final stages of a massive star's life, its core is like a great cosmic onion. At its center, the star is fusing the heaviest elements it can manage, perhaps silicon into iron. In a shell surrounding that, lighter elements are still fusing. And so on, in layers, all the way to the outer shells where hydrogen is still burning. The star becomes a stratified factory, simultaneously creating a whole suite of new elements that the universe had never seen before. But this process of creation has a limit. The star can build elements up the periodic table until it reaches iron. Iron is the most stable nucleus in the universe. To fuse all the elements lighter than iron, hydrogen, helium, carbon, oxygen, releases energy. This is the energy that holds the star up against the crush of its own gravity. But to fuse iron into something heavier does not release energy. It consumes it. Iron is the final ash of stellar fusion. It is the end of the line. When the core of a massive star turns to iron, its energy source is cut off. It can no longer fight against gravity. The core collapses, the star explodes in a supernova, and in that cataclysmic event, the final act of creation takes place. The explosion itself is so energetic, it unleashes a massive flood of neutrons and energy that can accomplish what the star's core never could. In the brief, violent seconds of the supernova, these neutrons are captured by the iron nuclei and other elements, rapidly building up all the elements heavier than iron. The silver in your jewelry, the gold in a vault, the uranium that powers nuclear reactors, all of these precious, heavy elements were created in the flash of a supernova explosion. And this explosion does one more crucial thing. It does not contain its creations. It blasts them outward, scattering this rich cocktail of newly forged elements far and wide into the interstellar medium. The carbon, the oxygen, the iron from the star's life, and the gold and silver from its death, are all seeded into the clouds of gas and dust that will form the next generation of stars. This is the great cycle of cosmic enrichment. Each generation of stars is born from material that is richer in heavy elements than the last. Our Sun is not a first-generation star. It is the child of many generations of stars that lived and died before it. It was born from a cloud already rich in carbon, oxygen, iron, and all the other elements. And that is why our solar system could form not just a gas giant, but small, rocky planets like Earth. So as you lie here, on the verge of sleep, understand this profound truth. You are not just living in the universe is living in you. The calcium in your bones, the iron in your blood, the oxygen in your lungs, every atom of your being, aside from the primordial hydrogen, was forged in the fiery heart of a star that lived and died billions of years ago. You are, in the most literal sense, made of stardust. We have seen how stars live and how they forge the elements that give the universe its substance. Now we must bear witness to their final act. The most dramatic and consequential moment of their existence, their death. When a star exhausts the fuel in its core, it embarks on a final, transformative journey. This is not simply an end, but a return. It is the moment the star gives back all it has created to the cosmos, in a final farewell that can be either a gentle whisper or a glorious roar. Breathe in, And let us first watch the quiet passing of a star like our Sun. After its long life on the main sequence, it swells into a red giant, a final, grand expression of its being. As its outer layers cool and expand, it begins to shed them, not in a violent explosion, but in a series of gentle pulses, like a slow, rhythmic exhalation. The star is letting go of its form, releasing its substance back into the void. This expanding cloud of gas, lit from within by the hot, dying core, forms a planetary nebula. Let your mind drift through one of these celestial ghosts. They are among the most beautiful and serene objects in the night sky. They are not chaotic, but possess an intricate, often symmetrical, structure. Some look like vast, cosmic eyes, others like the delicate wings of a butterfly, or a perfect, glowing ring. They are the star's last masterpiece, a final, ephemeral work of art sculpted from its own atmosphere. They are a testament to a life lived in balance, and a death of graceful dissolution. At the heart of this glowing shroud, the star's core remains. It is a white dwarf, a small, intensely hot, and incredibly dense object about the size of Earth. It has no more fuel to burn. It is a cosmic ember, shining only with the residual heat of 1 billion years of fusion. It is the star's quiet corpse, a diamond in the cosmos, destined to spend trillions of years slowly cooling, slowly fading, until its light is extinguished forever, leaving only a cold, dark remnant to drift silently through the interstellar night. This is the gentle path. But for stars born with great mass, the end is a far more spectacular and violent affair. A massive star, in its final moments, has an onion-layered core of heavy elements, with iron at its heart. Iron, the ash of stellar fusion, cannot provide the energy to fight gravity. The star's furnace is extinguished. In less than a second, the core, heavier than our Sun, collapses under its own staggering weight. Gravity, the force the star has battled its entire life, finally wins. This catastrophic collapse triggers a rebound of unimaginable power. The star detonates in a supernova explosion, one of the most energetic events in the universe. In a single, brilliant flash, the dying star can outshine its entire galaxy of billions of stars. It is a final, triumphant roar of light and energy, a cosmic firework that announces the death of a giant. This explosion rips through the star, blasting its layers, all the precious heavy elements it forged in its life and in its death, out into space at incredible speeds. The death of a massive star is the universe's primary distribution mechanism. It is this violent, beautiful act that seeds the cosmos with the materials necessary for rocky planets and for life itself. And what is left behind is one of two extraordinary objects. If the star was massive, the core's collapse is halted by the strange laws of quantum physics, forming a neutron star. This is an object only a few kilometers across, yet it contains more mass than our Sun. It is a single, city-sized atomic nucleus, so dense that a spoonful would weigh billions of tons. But if the original star was truly a titan among titans, even the laws of quantum physics cannot stop the collapse. Gravity overwhelms all other forces. The core collapses forever, shrinking to an infinitely dense point, a singularity, tearing a hole in the fabric of space-time itself. A black hole is born. It is the ultimate stellar remnant, an object whose gravitational pull is so strong that nothing, not even light, can escape. It is gravity's final, absolute victory. So as you drift deeper into stillness, reflect on these two farewells. One is a gradual release, a quiet fading into the night. The other is a spectacular blaze of glory that enriches the cosmos. But both are acts of giving. Both return their substance to the great clouds of gas and dust from which new stars will be born. The universe is a place of endless cycles, of death and rebirth. The end of one star is always the beginning of countless new possibilities. We have seen the universe filled with its first stars, brilliant and fleeting giants that seeded the cosmos with the elements of creation. But these stars were not destined to wander alone. They were born in clusters, and these clusters were the seeds of something far grander. We now pull our focus back to witness the slow, majestic, and collaborative construction of the great islands of light, the cosmic cities that we call galaxies. Breathe in, and imagine a universe filled with these small, nascent clusters of stars, each nestled within its invisible halo of dark matter. The cosmic web, that vast, unseen scaffolding, has now become the blueprint for cosmic construction. The densest nodes of this web, where the filaments of dark matter intersect, are exerting a powerful gravitational pull, drawing these first proto-galaxies towards one another. The era of galaxy formation has begun, a process of assembly that will span billions of years. The guiding principle of this era is gravity, the silent, patient architect. The first proto-galaxies, small and irregular, begin to drift towards each other, following the gravitational currents of the cosmic web. Imagine small streams flowing down a mountainside, inevitably merging to form larger rivers. So too did these small galaxies flow together. This process is not one of gentle merging, but of dramatic and transformative collisions. As two proto-galaxies collide, their individual structures are torn apart by tidal forces, their stars and gas clouds mixing in a chaotic, beautiful dance. These collisions trigger furious bursts of star formation. The vast clouds of hydrogen gas within each galaxy are compressed by the collision, sparking the birth of millions of new stars in a very short period of time. The merging galaxies light up with a brilliance that testifies to their violent and creative union. Over eons, through countless such mergers, galaxies grow. Smaller structures are cannibalized by larger ones, adding their stars, gas, and dark matter to the growing whole. This is the great hierarchical assembly of the cosmos, building from the small to the immense. But this growth is not unchecked. As these young galaxies blaze with the light of newborn, massive stars, they also create a powerful feedback. The intense radiation and strong stellar winds from these stars, along with the shock waves from their supernova explosions, can push back against gravity's pull. This energetic outflow can heat up the surrounding gas and even blow it out of the galaxy entirely, temporarily starving it of the fuel needed to form more stars. This is a delicate process of cosmic self-regulation. The galaxy's own creative fire prevents it from burning through all its material too quickly, ensuring a longer, more sustained period of evolution. Over billions of years, this dance of gravitational collapse and energetic feedback shapes the galaxies into the diverse and beautiful structures we see today. In sum, the chaotic energy of mergers settles down. Gas, as it is pulled into the growing galaxy, conserves its angular momentum, flattening into a vast, spinning disk. Density waves, rippling through this disk like waves on a pond, trigger the formation of new stars in graceful, sweeping arcs. In this way, the beautiful, ordered structure of a spiral galaxy, like our own Milky Way, is born from the chaotic mergers of its past. And at the heart of this entire process, another giant is growing. As galaxies merge, the black holes at their centers also fall together, eventually merging to form a single, larger black hole. Through the accretion of gas in these repeated mergers, a supermassive black hole grows at the center of every large galaxy, an anchor of immense gravity that stabilizes the orbits of the inner stars. The galaxy and its central black hole grow together, their evolutions inextricably linked in a cosmic partnership. As you rest, drifting in the darkness, picture this grand process of construction. Our own galaxy is a testament to this history. It is a metropolis built from the rubble of 100 smaller galaxies that have merged and contributed their stars to our own. It is a structure sculpted by the patient pull of gravity and the fiery breath of its own stars. It is a living, evolving city of light, still growing, still changing, on its long journey through the cosmos. The universe, in its grand and patient assembly, does not believe in uniformity. The chaotic dance of mergers and the delicate balance of feedback that we have witnessed do not produce a single, standard outcome. Instead, they have painted the cosmos with a breathtaking diversity of forms. Let us now drift through this celestial art gallery, to gaze upon the different types of galaxies, each a masterpiece with its own unique history and character. Breathe in, and let us first approach the most familiar and perhaps the most graceful of these forms, the spiral galaxy. Our own Milky Way is one such galaxy, a vast, spinning disk of stars, gas, and dust. At its heart lies a bright, dense central bulge, a sphere packed with older, cooler, reddish stars that have been orbiting the galactic core for billions of years. This is the old city center of the galaxy. And radiating out from this ancient heart are the majestic spiral arms. These are not static structures, but great, sweeping density waves, ghostly patterns that ripple through the galaxy's disk. As these waves pass through the clouds of interstellar gas and dust, they compress them, triggering the collapse that leads to the birth of new stars. The spiral arms are the galaxy's rivers of creation, its vibrant, youthful suburbs. They are rich with the raw materials for new suns, and they glow with the brilliant, blue-white light of hot, young stars and the beautiful pink and red hues of the emission nebulae those stars illuminate. To look at a spiral galaxy is to see a living, breathing city of stars, with a quiet, ancient core and bustling, creative arms, a place of both history and becoming. Now, let us drift away from the spiral's elegant disk and approach a different kind of cosmic structure, the elliptical galaxy. If the spiral is a bustling city, the elliptical is a serene and ancient kingdom. It lacks the flat disk and graceful arms of its spiral cousin. Instead, it is a vast, shimmering, three-dimensional ball of stars, ranging in shape from a perfect sphere to an elongated oval. As we draw closer, we notice a profound difference. The light here is softer, older, and predominantly yellow and red. The brilliant blue stars and glowing pink nebulae are almost entirely absent. That is because elliptical galaxies are composed almost exclusively of old stars. They contain very little gas and dust, the raw materials for star birth. Their era of creation is long past. They are, in a sense, retired galaxies, cosmic retirement homes where the stars will live out their long lives in quiet, stately orbits. Their smooth, uniform appearance is thought to be the result of a violent and chaotic past. Many ellipticals are believed to have been formed by the merger of two or more spiral galaxies, a colossal collision that used up all the gas in a final, brilliant burst of star formation and randomized the orbits of the stars, leaving behind this placid, settled, and ancient city of light. Let us now seek out the third main type, the wild ones of the cosmos, the irregular galaxies. As their name suggests, these galaxies have no defined shape. They are not spinning disks or smooth ovals. They are chaotic, clumpy, and asymmetrical. They are the beautiful accidents of the universe. Their disordered appearance is often the signature of a recent or ongoing traumatic event. Many irregular galaxies are the result of a close encounter or a collision with another galaxy, the gravitational forces of the interaction tearing their structure apart, flinging stars and gas into distorted streams and clumps. But this chaos is often incredibly fertile. These galaxies are typically rich in gas and dust, and the gravitational disruption they are undergoing can trigger intense bursts of star formation. They are like cosmic nurseries exploding with activity. To look at an irregular galaxy is to see a snapshot of cosmic evolution in action, a system in the midst of a great transformation, its future shape still unwritten. And as with any great classification, there are forms that exist in between. We see lenticular galaxies, which possess the central bulge and disk of a spiral, but have no arms. They are like spiral galaxies that have used up all their gas, their star formation having ceased, leaving them as smooth, lens-shaped objects, a bridge between the active spirals and the quiet ellipticals. This beautiful diversity of galactic forms is a storybook of cosmic history. Each shape is a clue to the galaxy's past, a history of quiet, isolated evolution, of violent, transformative mergers, or of recent, disruptive encounters. The universe is not a factory producing identical objects. It is a garden, where 1,000 different flowers bloom, each with its own story to tell. We have wandered through the cosmic gallery, gazing upon the magnificent diversity of galaxies. Now, it is time to come home. Let us turn our focus to one particular barred spiral galaxy, a beautiful city of 200 billion stars, our island in the cosmic ocean. We are going to tell the story of our own home, the Milky Way. Breathe deeply. This is not a distant, abstract history. This is our family story, the saga of our own cosmic origins. Our galaxy was not born in an instant, fully formed. It was built, piece by piece, over billions of years, in a grand process of cosmic construction, a story of mergers and acquisitions on a celestial scale. Our story begins not long after the Big Bang, about 13.6 billion years ago. In our local corner of the young universe, the cosmic web was taking shape. Within the dense nodes of this dark matter scaffolding, the first small proto-galaxies began to form. These were not mighty spirals, but small, clumpy collections of the first generation of stars. These were the building blocks of the Milky Way, the ancestral tribes that would come together to form our galactic nation. Guided by the relentless pull of gravity, these small proto-galaxies began to fall towards each other. They collided and merged, their stars and gas clouds mixing and mingling. With each merger, the central mass grew, its gravitational pull becoming ever stronger, drawing in yet more of its smaller neighbors. The stars from these consumed galaxies were not destroyed, but their orbits were randomized, and they were scattered into a vast, spherical cloud. This is the oldest part of our galaxy, the stellar halo. And within this halo, we can still see the most ancient relics of our galaxy's birth, the globular clusters. These are tight, spherical swarms of hundreds of thousands of old stars, the dense, surviving cores of the very first small galaxies that the Milky Way consumed. They are the fossilized bones of our galaxy's ancestors. After this initial, chaotic period of mergers formed the central bulge in the halo, the next phase of our galaxy's life began. Over billions of years, fresh gas from the intergalactic medium was drawn towards the growing Milky Way. But this gas did not just fall in randomly. Because it had a slight rotation, as it fell inward, it conserved its angular momentum, spinning faster and faster, and flattening into a vast, stable, rotating disk. This was the Great Settling. The galactic disk is the home of all the younger generations of stars, including our own sun. It is where the gas and dust from countless stellar life cycles has accumulated, providing the rich material for ongoing star formation. And within this disk, graceful density waves began to ripple through the gas, creating the beautiful spiral arms we see in images of other galaxies. These arms are not solid structures, but zones of compression, where the gas is squeezed just enough to trigger the birth of new, brilliant blue stars. Our sun currently resides in a smaller, partial arm called the Orion Spur, a relatively quiet suburb of our vast galactic city. And the story of our galaxy's construction is not over. The Milky Way is a living, evolving system. It is still growing, pulling in streams of gas from the void and continuing its practice of galactic cannibalism. Even now, we can see the Sagittarius dwarf galaxy being torn apart by our galaxy's tidal forces, its stars being stripped away and absorbed into the Milky Way's halo, another small galaxy adding its substance to our own. And as we look to the future, we see the next great chapter of our galaxy's life unfolding. Our nearest spiral neighbor, the great Andromeda Galaxy, is hurtling towards us. In about 4 billion years, our two majestic spiral galaxies will begin a cosmic dance, a slow-motion collision and merger that will last for hundreds of millions of years. The night sky of any future inhabitants of Earth will be a spectacular, changing canvas of distorted galactic arms and bursts of new star formation. Eventually, our two galaxies will merge completely, their stars and dark matter combining to form a new, even larger elliptical galaxy, which some have nicknamed Milkomeda. So as you rest here, feel the deep history of your location in the cosmos. You are living in a structure built from the remnants of ancient galaxies, in a disk that formed long after the first chaotic mergers, orbiting a star that is a relative newcomer. You are part of an immense, ongoing story of cosmic construction, a story with a deep past and a spectacular, transformative future. We have explored the grand structure of our Milky Way, a city of stars built over billions of years. Now let us journey to its very heart, to the downtown core of this cosmic metropolis, a place of extreme density, speed, and power. For at the center of our galaxy, and indeed at the center of almost every large galaxy, resides a hidden monarch, a gravitational anchor of unimaginable mass and mystery, a supermassive black hole. Breathe slowly, and let your mind travel 27,000 light-years to the center of the Milky Way. Here, amidst a dense swarm of ancient stars, lies Sagittarius A-, our galaxy's central black hole. It is a silent, invisible behemoth, containing the mass of 4 million suns, all compressed into a single point. It is the gravitational heart around which our entire galaxy revolves. And its relationship with the galaxy it inhabits is one of the most profound and symbiotic partnerships in the cosmos. For a long time, we thought of black holes as mere vacuum cleaners, passively consuming anything that strayed too close. But we have come to learn that they are active participants in their galaxy's evolution. There is a deep and mysterious connection between the size of a galaxy's central black hole and the size of its central bulge of stars. They seem to grow together, to evolve in lockstep, as if following a shared destiny. The black hole is not just a resident of the galaxy, it is a co-creator, a regulator, a king. Its most important role is that of a galactic thermostat, regulating the birth of new stars. As clouds of gas and dust drift towards the galactic center, they are captured by the black hole's immense gravity and form a swirling, incandescent whirlpool of matter called an accretion disk. As this matter spirals inward, it is heated to millions of degrees, shining more brightly than all the stars in the galaxy combined. This is the black hole, feeding. And when a black hole feeds actively, it pushes back. From the turbulent heart of this accretion disk, colossal jets of energy and radiation are launched far out into space, at nearly the speed of light. These powerful outflows sweep through the central regions of the galaxy like a hot wind, heating up the clouds of gas that would otherwise have cooled to form new stars. In some cases, this energetic feedback can blow the star-forming gas out of the galaxy altogether. This is the black hole's profound act of self-regulation. If too much gas begins to fall in, triggering a frenzy of star birth, the black hole wakes up, and its energetic outflow shuts the process down. It prevents the galaxy from using up all its creative fuel in one giant, early burst. It ensures that star formation is a slow, sustained, and lifelong process for the galaxy. It is the dark, destructive heart that, paradoxically, ensures the galaxy's long and creative life. The supermassive black hole also shapes the very dynamics of the galactic core. The stars that live closest to it are engaged in a frantic dance, whipping around the black hole at incredible speeds, their orbits dictated by its singular, immense gravity. The environment here is too extreme and chaotic for stars to form in the usual way, yet we see young stars here. A puzzle that tells us the rules of creation are different in the shadow of a black hole. Occasionally, the gravitational interplay here can be so violent that a star is captured and torn apart, or slingshot out of the galaxy entirely, a stellar exile cast out by its monarch. The origin of these giants remains a mystery. Did they begin as smaller black holes, formed from the collapse of the first stars, and grow over eons by consuming gas and merging with other black holes? Or were they born big, from the direct collapse of vast, primordial clouds of gas in the very early universe? We do not yet know the answer. So as you rest, picture this silent, powerful heart at the center of our galaxy. It is a region of ultimate consumption, yet it is the key to the galaxy's sustained creation. It is a paradox of destruction and life, a dark, sleeping dragon whose fiery breath shapes the destiny of 100 billion stars. We have told the story of how our galaxy was born. Now let us take a slower, deeper look at the home we inhabit today. Let us take a grand tour of the Milky Way's magnificent architecture, to understand the specific geography of our place in the cosmos. This is a journey through the avenues and suburbs of our own celestial city. Breathe, and let us begin at the very center. At the heart of the Milky Way lies the galactic bulge, a vast, densely packed sphere of stars. These are some of the oldest stars in our galaxy, ancient, reddish suns that have been orbiting the core for billions of years. It is a place of immense gravitational power and stellar density. And hidden within the very center of this bulge, shrouded in gas and dust, is the supermassive black hole, Sagittarius A-, the silent, gravitational monarch around which our entire galaxy turns. From this brilliant, ancient core, the main body of the galaxy extends outward. This is the galactic disk, a vast, flat, spinning plane of stars, gas, and dust, stretching 100,000 light-years from edge to edge. If the bulge is the old city center, the disk is the sprawling, vibrant metropolis itself. It is here that the majority of the galaxy's stars reside, including our own sun. And it is this disk that is graced with the galaxy's most beautiful feature, the spiral arms. These arms, with names like Perseus, Sagittarius, and Scutum Centaurus, are not solid structures. They are great, sweeping waves of higher density, rippling through the disk. As these waves move, they squeeze the interstellar gas and dust, triggering furious bursts of new star formation. The arms are the bright, bustling avenues of our galaxy, glowing with the brilliant blue light of hot, newborn stars and the rosy pink of the nebulae they illuminate. They are the creative heartlands of the Milky Way, when new suns and new worlds are being born at this very moment. And where are we in this vast metropolis? We do not live in the chaotic, high-radiation environment of the core, nor do we reside in one of the grand, major spiral arms. Our sun is located in a quieter, more peaceful neighborhood, a smaller, partial arm known as the Orion Spur. We are about 27,000 light-years from the galactic center, roughly 2/3 of the way to the edge. This relatively calm location has been a blessing, shielding our solar system from the frequent supernova explosions and intense gravitational forces found in the more crowded regions of the galaxy, and perhaps providing the long-term stability needed for life to evolve. Now let us pull our view out even further, beyond the luminous disk. Surrounding the entire flat plane of the galaxy is a vast, spherical cloud known as the stellar halo. This is the galaxy's ancient historical district. It is sparsely populated with very old stars and the beautiful globular clusters, the fossilized remnants of the first small galaxies the Milky Way consumed in its youth. The halo is also where the vast majority of the galaxy's mass resides, not in stars, but in the invisible, enigmatic form of dark matter, the gravitational glue that holds our entire galactic city together. And our galaxy is not alone. Like a great capital city with its own surrounding towns, the Milky Way is attended by a retinue of smaller, satellite galaxies. The most famous of these, visible from Earth's southern hemisphere, are the Large and Small Magellanic Clouds. These are irregular dwarf galaxies, gravitationally bound to the Milky Way, engaged in a long, slow dance with us. Over billions of years, they will likely be absorbed, their stars and gas becoming the newest citizens of our ever-growing galactic home. So as you rest here, feel the comfort of your place. You are in a quiet neighborhood of a majestic spiral city. You are surrounded by a deep and ancient history, and you are part of a living, evolving system on a shared journey through the vastness of cosmic space. We have toured the grand architecture of our Milky Way, from its chaotic core to its serene halo. We feel its size, its structure, its living, breathing nature. But there is another dimension to our home that we must now explore, its dimension in time. How old is this celestial city we inhabit? What is the story of its endurance? Breathe slowly, and let your mind embrace the concept of deep time. The age of our galaxy, the Milky Way, as pieced together by generations of astronomers, is staggering. It is approximately 13.6 billion years old. To put this in perspective, the universe itself is about 13.8 billion years old. This means that our galaxy is not a newcomer on the cosmic stage. It is a true elder, one of the first great galaxies to form, its origins stretching back to the very dawn of the cosmos. But how can we possibly know this? How do we date a structure of such immense scale and age? We do it through a form of cosmic archaeology. We search for the oldest residents of our galactic city and study them for clues about their birth. These oldest residents are the most ancient stars, and they hold the secrets of the galaxy's age in their very light. The key to reading this history lies in a star's chemical composition. The early universe, as we know, contained only hydrogen and helium. The first stars were forged from this pure, pristine material. As they lived and died, they created heavier elements, carbon, oxygen, iron, and scattered them into space. Each subsequent generation of stars was born from a cloud of gas that was slightly more enriched with these heavy elements. In astronomical terms, these heavy elements are called metals. A star's metallicity, its abundance of heavy elements, is therefore like a cosmic birth certificate. A star rich in metals is young, a relative newcomer. A star with very, very few metals must be ancient, a relic from a time before the universe had been significantly enriched. And so astronomers search for these metal-poor stars. And they find them, not in the bustling, youthful disk of the galaxy where we live, but in its most ancient districts, the vast, spherical halo and the tight, beautiful globular clusters. These are the quiet outskirts and historical centers of our galaxy, populated by the survivors of the very first waves of star formation. By carefully measuring the age of these ancient, metal-poor stars, we can put a minimum age on the galaxy that contains them. And that age is 13.6 billion years. This stellar dating is confirmed by our other cosmic measurements. The age we derive from these ancient stars fits perfectly with the age of the universe we calculate from the afterglow of the Big Bang, the cosmic microwave background. The story is consistent. Our galaxy began its long process of assembly very shortly after time itself began. This immense age tells us that our galaxy's history is a long and epic saga of gradual assembly, of countless mergers and slow accretion that have built it up over almost the entire lifespan of the universe. And it gives us a profound sense of perspective on our own place within it. Our Sun and the solar system are only about 4.6 billion years old. We are relative newcomers. Our star was born into a galaxy that was already ancient, a mature and well-established city with a history that stretched back 9 billion years before our Sun ever ignited. As you lie here, on the edge of sleep, feel the depth of this history beneath you. You are living inside a structure that is almost as old as time itself. You are a fleeting resident in an ancient, enduring city of stars, a city that was old before our world was even born. This profound antiquity is part of your cosmic heritage. We have toured the vast structure of our galaxy and contemplated its immense age. Now, let us embark on a journey to its most mysterious and extreme region. We are traveling inward, past the quiet suburbs of the Orion Spur, through the bright, bustling spiral arms, to the very heart of the Milky Way. We are going to the galactic center. Breathe in, and let your imagination travel with me across 27,000 light-years of space. As we approach the core, we find our view is blocked. From our vantage point on Earth, a thick, impenetrable curtain of interstellar gas and dust hangs between us and the galactic heart, hiding it from our sight in visible light. For centuries, what lay at the center of our galaxy was a complete mystery. But humanity has devised new ways of seeing. Using telescopes that can detect infrared, radio, and X-ray light, we can now pierce this dusty veil and look upon the chaotic, brilliant world that lies within. What we see is a place unlike any other. The center of our galaxy is a dazzling, crowded, and violent swarm of stars. Millions of stars are packed into a volume of space that would fit only a handful in our own quiet neighborhood. They orbit the center at incredible speeds, like a frantic hive of celestial bees. Here, we see ancient, red giant stars on long, looping orbits, their journeys having begun billions of years ago. And paradoxically, we also see brilliant, young, blue stars, blazing with an intensity that tells us they were born recently. And this is a profound mystery. For at the very center of this swarm lies the supermassive black hole, Sagittarius A-, the 4 million solar mass anchor of our galaxy. The tidal forces here, the gravitational shear from the black hole, should be far too powerful to allow a fragile cloud of gas to collapse and form a star. These forces should tear such a cloud to shreds. And yet, young stars exist here. Their presence tells us that star formation in this extreme environment must follow different, more violent rules than it does in the quiet disk of the galaxy. It is a puzzle that astronomers are still working to solve. Surrounding the black hole is a swirling maelstrom of activity. Vast clouds of gas and dust drift through the core, some glowing with the heat of the intense radiation, others destined to be stretched into spaghetti-like strands as they are pulled into the black hole's accretion disk. We also see strange, beautiful structures found nowhere else, enormous, glowing filaments of magnetic energy, hundreds of light-years long, that cut through the region, their origin and purpose still a deep mystery. And the center is not quiet. From the immediate vicinity of the black hole, we detect powerful flares of X-ray and radio light. These are the brief, energetic flashes that occur when a small cloud of gas or an unfortunate star gets too close and is consumed by the sleeping giant. They are the hiccups of a black hole snacking, a reminder of the immense power that lies dormant at the galaxy's heart. As you lie here, enveloped in the peace of your room, picture this distant, chaotic core. It is the most extreme environment in our galaxy, a cosmic laboratory where the laws of physics are pushed to their limits. It is a place of mystery, of impossible star birth, and of unimaginable gravitational power. And yet, this violent, brilliant, chaotic heart is the anchor that provides the stability for the entire, vast, graceful structure of the Milky Way. It is the storm at the center of the calm. The engine room of our galactic city. We have journeyed through our galaxy's deep past and toured its present-day structure. Now let us cast our gaze forward, into the deep future, to contemplate the ultimate destiny of our cosmic home. The story of the Milky Way is not over. Its grandest and final chapters are yet to be written across the canvas of cosmic time. Breathe, and let your mind float forward into time. For now, The Milky Way will continue its serene existence, its spiral arms continuing to churn out new stars, its disk a hub of cosmic life. But another great galaxy is moving through the darkness towards us. Our nearest spiral neighbor, the majestic Andromeda Galaxy, is on a collision course with the Milky Way. It is currently 2.5 million light-years away, but it is closing the distance at a speed of over 100 kilometers every second. This is not a possibility, it is a gravitational certainty. In about 4 billion years, our galaxies will meet. Imagine the night sky of a world in that distant future. For millions of years, the Andromeda Galaxy would have grown larger and more spectacular, swelling until it fills the sky, a vast, pinwheeling island of light. Then, the first tendrils of our galaxies would touch. This will not be a crash of solid objects. The space between stars is so immense that it is almost certain no two stars will collide. Instead, it will be a graceful and chaotic ballet of gravity. The two galaxies will pass through each other, their mutual gravity distorting their beautiful spiral shapes, flinging long tails of stars and gas out into the void. They will pull apart, and then gravity will draw them back together again, for a second and then a third pass. During these encounters, the vast clouds of gas and dust from each galaxy will slam into each other, triggering a final, spectacular burst of star formation. The merging galaxies will light up, becoming a brilliant, chaotic starburst galaxy, one of the brightest objects in the local universe. And at the heart of this merger, the two supermassive black holes, Sagittarius A and its counterpart from Andromeda, will begin to orbit each other, spiraling closer and closer over millions of years. Eventually, they too will merge into a single, even more massive black hole, a union that will send a powerful shudder through the fabric of space-time itself in the form of gravitational waves. After this long, transformative dance, the chaos will subside. The two spiral galaxies will have become one. The end result will be a new, gigantic, and placid elliptical galaxy, a vast, shimmering ball of stars, the product of this cosmic union. But the story continues, moving into a timescale far grander. Over the next trillions of years, the gas in this new galaxy will be used up. Star formation will cease. One by one, the existing stars will exhaust their fuel and die. The massive stars will have long since exploded, leaving behind black holes and neutron stars. The sun-like stars will shed their layers and fade into cold, dark white dwarfs. The galaxy will grow dim. Its light will go out. It will become a dark galaxy, a silent cemetery of stellar remnants, drifting in the void. And the universe itself will be growing ever more lonely. The relentless, accelerating expansion of the cosmos, driven by dark energy, will be pushing all other distant galaxies away from us at incredible speeds. They will recede from view, their light stretched into invisibility, until they cross a cosmic horizon from which they can never be seen again. Our local group of galaxies, bound by gravity, will remain as a single, isolated island. But the rest of the universe will have vanished into an ever-expanding, ever-darkening abyss. Our great galaxy will be left alone in the cold and the dark, a final, quiet remnant of a once brilliant cosmos. This is the ultimate destiny of our home. It is a story of a final, glorious merger, followed by a long, slow, and peaceful fade into darkness and isolation. We are lucky to be alive now in the vibrant, star-forming, middle-aged era of our galaxy's life, a brief, beautiful moment before its long twilight begins. Of course. Let us begin the final segment. Our long journey through space and time is coming to its gentle close. We have drifted from the very first instant of creation, through the forging of the first particles and the separation of the great forces. We have witnessed the birth of the first atoms, the lifting of the cosmic fog, and the long, quiet night of the Dark Ages. We have watched the first stars ignite like candles in the void, live their brilliant lives, and die in acts of profound creation. We have seen how they gathered into the great, beautiful island cities we call galaxies, and we have followed the story of our own Milky Way, from its ancient past to its distant, transformative future. We have learned so much. And yet we end, as we must, in a state of profound and beautiful mystery. We are surrounded by questions that touch the very edge of our understanding. Could all of this immensity, all of this intricate order and complexity, truly have emerged from what appears to be nothing? Is there a missing chapter to this story, an unknown principle or a hidden reality that we have not yet discovered? And perhaps the most humbling question of all, are we, as a species, even capable of comprehending the answers we seek? The universe does not offer easy answers. It offers something far more precious, a sense of wonder, and a sense of connection. As you lie here now, at the end of this journey, feel the truth of that connection in your own being. The carbon that forms the architecture of your cells was forged in the heart of a star. The oxygen you are breathing with each slow, steady breath was created in a stellar forge. The iron in your blood, which carries that oxygen through your body, was born in the spectacular, final explosion of a massive star, billions of years ago. You are not merely living on a planet that is part of the universe. The universe is living in you. You are a small, temporary, but beautiful collection of its stardust, animated for a brief time with the remarkable gift of consciousness. You are a way for the cosmos to know itself. The mind with which you have imagined this journey, the birth of space, the dance of galaxies, is itself a product of that very journey. That is the deepest and most beautiful mystery of all. And now, it is time to let these thoughts go. Let the vast story of the cosmos dissolve. Let the images of stars and galaxies fade, like embers in a dying fire. There is nothing left to learn, nothing left to explore, only to be. Be still. Feel the gentle pull of gravity, your own small connection to the fabric of space-time. Feel the quiet of the room around you, a tiny, peaceful pocket in an immense and silent universe. Your journey is over. Let your awareness soften and blur. Let go of the story, and drift now on the quiet, dark river of sleep. The universe will continue its silent, majestic dance while you rest. And you are a part of it. Sleep now. Good night.